Okay, so welcome everyone again. It's a great pleasure to have Sasha Petrov from IAS and Clay Math and soon MIT to give the first of his 4 lectures on p-adic Riemann-Hilbert.
Great. Thanks very much for having me, and thank you all for coming. Please do ask questions at any time. Don't hesitate. My actual plan is to talk about a certain topic in p-adic Hodge theory, but today I'll mostly kind of try to advertise why you might care about this, even if you don't inherently care about p-adic numbers. So we've heard a lot about local systems today, and so as we've seen, one source of local systems was homology of families of varieties. So let me just start off over complex numbers. So suppose I had some base variety, which I'll call S. And let's say it was over complex numbers, and maybe it was smooth. If I have a family of varieties over that, which say was smooth and proper, so that cohomology does form a local system, then I can just form in the topological category the higher derived direct images of the constant sheaf, and these are local systems or on the underlying base. So this is really just a topological notion. It lives on the underlying topological space of my base scheme S. And so, as Daniel already mentioned, it's a question which you can ask. Is there anything special about these local systems coming from families of varieties among all local systems? And if there is, then is there something qualitative we can say about that? So let me just introduce the following terminology. And here I worked with Z coefficients. Let me just allow myself slightly more generality. So suppose I have some commutative ring of coefficients. But really, I think the only actual instances which will appear will be either Z, as I already seen, ZP, and sometimes QP or QP bar. By a local system, I'll just mean, I think I'll sometimes forget to specify this, but always mean a local system of free finite rank A modules. And so, as we've seen multiple times today, so local systems of free A modules of some rank n on my space S. These were locally constant sheaves, and let me just assume that my S was connected. To say this, then these are the same as conjugacy classes of homomorphisms into the general linear group from the fundamental group, if I choose a base plate. So up to conjugation. So here, of course, implicitly up to isomorphism, but here it's up to conjugation by elements of geometry. And if I had a local system L here, I would typically denote the associated representation by rho L. Okay? And so let me define the following special class of local systems, which arise from homology of varieties. So the definition is that local system of A modules L on C points of my S is of geometric origin. If it comes from homology of varieties, but in the following slightly weaker sense than just being equal to one of these, which turns out to be a slightly more natural generality. So if I can first of all restrict to some open in my base variety S, say just Zariski open, and then I can find some family over that hue. Such that if I restrict L to a local system on this open, then there it will be a subquotient of the, rather it will be a direct summand of cohomology of this path. Well, when I take it with A coefficients, whatever my A is. Right, so I'm just allowing not a local system distribution, which is not the whole cohomology space, but only a direct summand of that. And I'm also allowing that there be a smooth proper morphism only over an open. Maybe it extends to the whole S, and maybe there's some singular fibers, and this is okay with me. And it's maybe right now it's not even so crucial why. Let's not pay too much attention to this modification, but let me just say that it's in a way harmless, because restricting a local system from S to U does not lose much information about the local system, because fundamental group of U is always surjects on the fundamental group of S. Right? Because U is a risky open, it's a very large open. It's a complement to a closed subset. And so at least the isomorphism class of L is preserved by this operation. All right? And so I could ask, so this is my class of local systems that I'll care about, and I could ask, can I classify them or say something about them? So, well, this might seem like a fairly specific question, and, but one reason is that I personally find it interesting is that when you're starting to answer it, you immediately run into a certain fundamental question. So let's kind of think about this. How could we ever answer such a question? So answering this question would involve having a method for disproving that some local system comes from geometry. So someone gives us a local system, and then we somehow convince them that there is no variety which could give rise to it. So you would have to, in a way, you would have to run through all varieties to check. So, but how could you efficiently disprove such a thing? So one way is you could find some additional structure which is present on such a local system, and then check that for some local systems the structure is not there. Yeah. And so, well, to answer this question, you have to, at least along these lines, you would first need to answer the question of what are the additional structures which exist on cohomology of varieties and families of varieties. And Daniel gave us a optimistically long list of such structures. And well, today, and somehow essentially for all of my talks, I'll actually focus on one specific structure, which already implicitly appeared in Lab's talk. But before I go into there, let me kind of make maybe another basic remark about this notion, is that this question is really, I could have asked this in any geometric setting. I could have asked it in differential geometry and complex geometry, but it's really only interesting in algebraic geometry. So a remark is that if I allowed myself even to work in the category of complex manifolds, this question would not be interesting. So for any Z local system on S of C, there exists a family of complex manifolds. So let's say S proper fibration of complex manifolds. Since this is really, I view S as a complex manifold here rather than as a variety, let me just write the set of C points here. There exists a family such that L is a direct summand already of the first relative cohomology. Okay, so let me not say how you construct these families. It's a pleasant thing to think through. But if you just trust me on that, then this is saying that really, if I allowed myself to work even, well, not with the most lax notion of geometry, the answer would be essentially all. Okay. So if the answer is going to be more interesting in algebraic category, then it has to use something specific to algebraic varieties. And so what are the special structures of cohomology of algebraic varieties which don't exist on arbitrary complex manifolds or topological spaces? And so there's essentially two avenues. You could either, there are such structures coming from Hodge theory, or there are such structures coming from arithmetic geometry using the Gull action. And I'll focus on the latter. So let me introduce this structure. Are there any questions so far? So let me make the following definition, and then it will be somewhat involved, but then we'll talk carefully about it. So definition. So here, let me now restrict my coefficients to either ZP, QP, or QP bar. Let me just say it for ZP coefficients, and then the same definition verbatim will make sense for a QP or a QP bar. So a ZP local system L on S of C is called arithmetic. Again, it's some condition on local systems in this topological space. Now with these p-adic coefficients, where p is some prime which I fixed once and for all, which was already in my title, I suppose. So it's arithmetic if there exists a model for your variety S over some finally generated field. So if there exists a subfield of C which is finally generated over Q, and a variety S0 which is the descent of minus. So far, such a pair I can always find by the argument that Gleb explained, that S, it's a smooth variety patched from some affines, so I should just descend those affines and descend the patching functions. And this all takes only finitely many elements of complex numbers. But now the condition of the local system is that the local system extends to an entire local system on this S0. And L extends to a local system. Let me introduce a name for it, say L tilde, on this S0. So if you prefer to think about local systems in terms of representations of fundamental groups, then what this is saying is that I started with a representation of the topological fundamental group with respect to some base point, say which came from say from a C point of my S. So I had a representation in the GLN of ZP corresponding to this local system L. But now I'm saying that if I can find this spreading out of S such that this representation extends to the representation of the fundamental group of that spreading out. And let me just break this out in two steps. So I can consider the fundamental group of this as 0, which Gleb introduced. And ultimately the condition is that there exists a representation here. And its compatibility with the original representation is that, as we saw, this naturally maps to the Ital fundamental group of the same scheme S. This map exhibits this profinite group as the profinite completion of this discrete group, which is the topological fundamental group. And then in fact, the Ital fundamental group in characteristic 0 does not change if you extend your base field to another algebraically closed field. And so this is the same as the Ital fundamental group of my S0 over F bar. And this has a natural map to S0. And so the condition here is that this diagram should commute. So I started with a representation of a topological fundamental group. Since the target group is profinite, in fact, it's always for free to extend it to this group, which is a profinite completion. And really, the content of this condition is that I'm able to extend it from this group to this larger group, which now, the relation between these two groups is that, I think as Gleb told us, is that one is an extension of the Galois group of my field F by the other. So there's a fundamental exact sequence, and so my abstract situation is that I have a representation of a subgroup, and I'm trying to extend it to a larger group. Right? So why does this condition come up? Let me first say why it's relevant for me, and we essentially, in a way Gleb already explained this, and then we'll start contemplating this condition. Are there any questions about this definition? Please.
Is this independent of the choice of spreading out?
Right, a good question. So I'd really like to, well, in the way I stated it now, I really want to allow all possible spreading out. And in a second, I'll reformulate this condition as something which holds for any particular spreading, but it will just sound slightly differently. So, yeah. Because it might very well happen that you can extend a representation to a representation of sum by 1 of S0, you find over some field F, but if you try to descend to some smaller field, for instance, even if the difference is just a finite extension of the Gauss group of finite extension, there might still be instruction to descending it further. Right? So why does this come up? Because a remark, or a fact, is that, right, so here I stated it for ZP local systems, and let me just, to save space for myself, let me say that there is a completely analogous condition for QP bar local systems. QP or QP bar local systems. And oh yeah, I should say, I'm not quite sure who was the first to come up with this notion. I personally learned from this, at least I learned this terminology from one of the papers of Daniel. If you want to clarify these things.
Yeah, maybe.
I think,
Yeah, I mean, I don't know if I was the first person to use the word, but I'm definitely about the ideas here in Simpsons.
Right. Right, the condition appears for Simpson. But I think it's an apt term. Okay. So the remark is that if you take any QP bar local system which is of geometric origin, then it is arithmetic. So where does this come from? So suppose the condition of being geometric origin, as I stated it, it's something happening purely over complex numbers, right? I have this family over complex numbers. But now the crucial step which was used in proof of Grothendieck's quasi-independent monodromy theorem, which Gleb explained, was that we could always descend this family to some finally generated field along with this S. And then by the comparison between singular homology and Natal homology, this whole local system would also descend to a Natal local system over that spreading S. Then I defined local systems of geometric origin as direct summons of these. And there's a little argument still needed to prove that still every direct summon has this property that it extends to a Natal local system. And to make this argument easier, I'm working with QP bar local systems here. Let me not go over it right now at the board, but please ask me if you're curious. Right? So up to this issue of the direct summons, this is what Gleb explained. Really, because what separates algebraic varieties from complex manifolds is that we can spread out algebraic varieties to some arithmetically interesting basis, and then this gives me this condition on the monodromy. Now, is this condition really interesting or non-trivial? As Gleb explained to us, the answer is yes. So an example is that if my base variety was GM, well, the group structure is not a word here, let me rather write it as A1 minus the origin. Then being arithmetic, so, and so if and only if the associated representation for the image of, well, any generator of this group, which is just Z, generated by some loop gamma, rel of this gamma is a matrix which is quasi-uniform. So Gleb explained that if L was arithmetic, then, so a priori, if I just have a representation of the fundamental group of GM, it's just a homomorphism from Z into GLN of whatever my field is, say QP bar. So it's just a single operator, no constraints. But then the magic was that because of this short exact sequence being so so far from being a direct product, the condition of extendability forced the eigenvalues to be roots of unity. And in fact, the converse is also true. So if you have any quasi-uniform matrix, you can eventually realize this in an arithmetic local system. You just have to write down one example. So you see that really, already in this case, being arithmetic is a fairly stringent condition, right? It forces your eigenvalues to be roots of unity. Okay. So, but originally the question, first of all, are there any questions about what I said? Please.
Is there a reason why here you have a zero key open, but on the arithmetic side you don't choose a zero key open?
Yeah, okay, very good question. Very good question. So here I didn't have to. If I just demanded this condition on a zero key open, it would still be true for the original local system. Because, for instance, one way, at least for semi-simple local systems, you can rephrase this condition as saying that the character of my representation is invariant under Galois conjugation. And so, if I were to precompose this with fundamental group of some open, this would be a surjection. And so if I could check that the character of this precomposed representation was still invariant under Galois conjugation, this would be true for the original. In a way, this feature is a motivation for having an open there. Because for, actually, I think all conditions I'm aware of, such as arithmeticity or having a variation of Hodge structures, if you know it on an open, you immediately know it on the whole space. In fact, I don't think I know of an example which would show that this, provably show that this condition would change if I didn't have an open. If someone knows such an example, I'd be very curious.
A provable example of what?
So I could have made this definition without a U, so just demand that there was a smooth proper morphism over all of S. Whether this would be a different definition. But somehow in all kind of most interesting situations where you can actually prove that something is of geometric origin, you actually prove this thing.
Let me just conjecture they're the same.
They're the same. Oh, okay, great, yeah, yeah. Okay.
How would you ever?
Can we read it out?
It's recorded.
Oh yeah. Oh, that would be too strong. Great. That's pretty bold. Yeah, okay, maybe I'll ask you.
In mixed covers.
Well, you really, there might be.
Because you might be able to find some totally different apps.
Right. That's the. It's true that neuron for each criterion fails for some classes of varieties. Let's talk about this. Yeah. So, all right. Were there any other questions? So we see that here it was a fairly stringent condition. Then I said that my original goal was to try to answer this question. Okay? And so here we came up with a necessary condition. So arithmeticity is a necessary condition. And it was also pretty stringent, which is good for us. And it turns out that there's a conjecture, which, and one of my goals will be to try to present some evidence for this, which you can loosely label relative Fontaine-Mazur conjecture. Is that every semi-simple, so semi-simple means the direct sum of irreducible local systems. If you bar local system, so, wait, what is it? Sorry, I mean, if L is arithmetic, it's arithmetic even only if it's of geometric origin. Okay, so we just discussed that the leftward implication is true thanks to the theory of Vital homology, and the conjecture is that if somehow you happen to be able to extend your representation to as representation of this algebraic fundamental group of a spreading out, then there should be some geometric family responsible for that. Okay. And well, here I include semi-simplicity just because I defined local systems of geometric origin as arising from homology of smooth proper families. And it's a consequence of Hodge theory, which we might see towards the end of this conference, that those are always semi-simple. There are interesting things to say about non-semi-simple local systems, but let me just restrict it to this case. All right. So, why would you believe this? So let's consider an example. Oh, now I have two conjectures, so now it's hard to tell which one I'll be referring to. Okay. So, if S was again A1 minus 0, then the conjecture on the left is true. And this is essentially what Gleb explained to us. Because there, we know that arithmetic local systems are, well, again, local systems anyway are just, the data of a local system is the data of a single conjugacy class of a matrix. And they all have to be quasi-unibonded, so eigenvalues have to be roots of unity. Now, if I'm working with semi-simple local systems, again, it's single operator, so it should just be diagonalizable operators. So, arithmetic, in this case, implies that L has finite monodromy. Which just means that it means that it's trivialized by a finite L cover. Right, because if I have a representation of this fundamental group, which is diagonalizable and all eigenvalues are roots of unity, it means it's a matrix such that if I raise it into a large enough power, into a divisible enough power, then it will be a trivial matrix, it will be the identity matrix. And so just passing to a cover of degree, which is again divisible enough, would give me this. But now a local system of finite monodromy, it does come from geometry, because if there is this finite L cover X to S, trivializing it, then the local system arises in relative zero of homology of this cover. So L is a direct summand. Will just be plain zero of push forward along this path. Right? So, and this is really not the most interesting case. So there's no interesting geometry, it's really just a finite L. So here, in this particular case, the arithmeticity was so strong of a condition that it gave me. Right? So in this case, it's true. But of course, this as soon as you go to hyperbolic curves, for instance, if you puncture this once more, I think this case becomes as interesting as the general case. And it's completely open to the best of my knowledge. Okay. So, why would you believe in such a statement? Before I say more about it, are there any further questions? Okay, so Daniel already emphasized this analogy, which I also like very much, between non-abelian conjectures about non-abelian cohomology and more classical conjectures about plane cohomology. And let me elucidate the fact that this conjecture can also be viewed as a literal non-abelian analog of Tate conjecture. Please.
So it's like in the definition of this geometric origin,
Yeah.
you're using like the existence of this open.
Oh, you mean how is being used?
So I might be confused because like there are certain like non-finite monomers, right? Like geometric origin.
One where? Sorry, but it should be a local system on the whole GM.
Yes.
So one of the outputs of this is very hard to come up with interesting families of varieties over A1 with just one puncture. Interesting from the point of view of their cohomology. did I answer your question? Right. So let me make a parallel between this conjecture and the Tate conjecture, which might also clarify the dependence on the spreading out. So what is this? Okay, so what is a local system? Let me just rewrite the set of local systems in a slightly different way. So as I said, at least for ZP local systems, the passage between a topological local system and a Natal local system over an algebraically closed field is really harmless. It happens automatically. So let me assume that I'm already working with QP bar local systems. On this S0, they change to its algebraic code. Right, so maybe I chose some spreading out over some particular field. So this is the same, if you like, you can just take this as a definition of the right-hand side. As first homology of this variety of RF bar with non-abelian coefficients. Now with coefficients in this topological group GLN of QP bar. So let's say rank n local systems. And you can just take this as a definition of the right-hand side to be the first continuous group cohomology of the fundamental group with coefficients in this non-abelian group. Which is really, with respect to the trivial actions, are really just the conjugacy classes of representations. But now, what's this? The additional very interesting structure is that there is, by functionality, there is an action of the Galois group of F on this, right? Because it was acting on the scheme S0 over F bar. Just because the scheme king is a base change from something over F. So now it's a little argument, but if I have a local system, then L is arithmetic. As stated there, so for some spreading out. If and only if its class in this group has finite orbit under this Galois action. So let me just denote this. It's isomorphism class in this set. Right, if L was arithmetic, literally with respect to this particular spreading out, then this class would literally be fixed, because then this representation would extend from this subgroup to this group, and then, well, conjugation by the Galois would act by inner automorphisms of this group, so it would not change the isomorphism class of the representation. But in general, there is, it's a little argument that if you have a spreading out, sorry, if you have if it's arithmetic with respect to some other spreading out, then this is still true for if you relax this to a finite orbit condition. Okay, but now what's the resemblance of the Tate conjecture? So let me just write next to it the Tate conjecture, which you can state as follows. So I'll just state it. Let me just assume for simplicity that my variety was proper. Assume that is smooth proper. Then there is a map from algebraic cycles of codimension I on S. This is all still happening over complex numbers. Into Ital homology of S, but this I might as well replace it by Ital homology of this S0 over F bar. And to make it completely canonical, let me take the Ital homology with coefficients in the Tate twist. And since this is codimension I cycles. So this is just an abelian group, but since I'm mapping to a QP vector space, let me translate it with QP. And let me call this the cycle class. And then the Tate conjecture states that the image of this QP linearized cycle class map is literally the set of classes here which have finite orbit under the Galois. because, well, here I'm talking about algebraic cycles on my variety over complex numbers, and I can always spread out this cycle to some finitely, to a model of minus 0 over some finitely generated field, and there's again a little argument needed to reduce this to this case where this spreading out is defined over a literally finite extension. But in any case, what I just said would prove that this cycle class map maps inside the group of elements which do have finite orbit, and then they conjecture that actually all such classes satisfying this purely homological condition, homology classes, they are explained by some physical algebraic cycle, or QP-linear combination of those. And in this way, the conjecture on the second board has a similar flavor. So any abstract representation of the fundamental group, which happens to extend to this arithmetic fundamental group, should be explained by some family of operators. Right? And hopefully we'll hear more from Daniel about this analogy, but I think it's quite fruitful.
Are these cycles defined over that far?
Right. That's a very good question. So I'm saying it doesn't matter for the purposes of the image of the cycle class map. Because, so if it was defined over complex numbers, then it's defined over some finally generated extension of it. Then I can find a spreading where I can then specialize to, and then I can specialize to a certain point of the spreading, which would be defined over a finite extension of f. So I'm saying I could have put f bar here, and the image would not have changed. It's an untrue argument. I get it. I can explain it more carefully later. Right. Any other questions?
Just please make sure I understand. So if like you have a representation of I1 in L that's zero, then like if the representation extends to this like arithmetic thing, is it actually like preserved under G? Is the orbit like actually?
Right. Exactly.
It's only this direct summit that makes it have finite orbit, not like true.
Oh, sorry. The finite orbit just comes from the fact that here, well, that as well. But also here, I committed myself to a particular spreading out.
Okay.
But it could have been defined over some larger extent.
Okay. And sorry, asking about this definition again, arithmetic, you don't even ask for direct summit. There's no direct summit.
Right. You could have asked it, and for QP bar coefficients, it would have been the same condition.
Okay.
Again, because of this freedom of, I mean, what you said at the beginning, because of this freedom to extend the field F. Because, well, if I have an arithmetic local system which gets split into several pieces, then each of them might not be quite extendable to the arithmetic fundamental group over a given field F, because the outer action of the Galois group might permute the isomorphic classes. But if I pass the finite extension, then thanks. Again, I think one of the papers by Daniel was a good reference for these things. I can tell you which.
Can I ask a question just about the, in the
Yeah.
Fontaine-Mazur, there's like a Durand condition, is that sort of automatically proven with this arithmetic?
Yeah, that's what I'll try to explain. That's the key point. Right. So actually, let me thank you for this segue into the second last part of my talk. So I started by saying that so you broke this conjecture, but let's try to be skeptical. And one way to be skeptical about it is what I announced at the beginning. There are other structures which are present with the homology of varieties. And so if I'm going to believe this conjecture, in particular, I'm going to believe that if I'm just arithmetic, this really Galois theoretic condition, then all those other structures are also present. But one of those structures is a variation of Hodge structures. So if you haven't thought much about it, I think tomorrow we'll have a pre-talk about that. So, but for now, I'll say explicitly all I need about variations of Hodge structures. So let me write it here. So if conjecture holds, then for any semi-simple arithmetic L, should underlie a variation of Hodge structures. So maybe for that to literally make sense, I have to choose an embedding of QP bar into complex numbers, and then if I cook out a C local system out of it, then this should have a complex variation of Hodge structures. Right? But where would it come from? And in fact, there is one of the most impressive applications of p-adic Hodge theory is exactly producing statements like of this form. That sometimes, using the purely arithmetic data of a Galois action, you can recover some piece of structure which has a Hodge theoretic flavor. And let me give one example of such a situation. And we'll talk more about this tomorrow, I think in Alice's talk and in mine. So here's what p-adic Hodge theory gives us. So, alright, it's the same prime as the one which I had before. So, suppose I had some, let's say, smooth proper variety over QP. Then I could take its adult homology in some degree. Let's see with, again, the very same QP coefficients. And it's a feature of p-adic Hodge theory that it becomes very interesting to consider varieties over QP, where I take homology with coefficients which involve the very same prime. So it's exactly the setting which in a way, so this is a representation of the Galois group of QP. And I could ask, how much does this representation remember about other homological invariants of this variety? And it turns out that it does remember quite a lot. So there's a function which we'll define tomorrow called d de Rham, which goes from all representations of the Galois group of QP. And when I say representations, I might forget to say this explicitly, it's always finite dimensional representations. There is a pointer to the following in the algebraic data. The vector space is over QP. Let me call this vector space V. With a filtration. And the usual convention is that it's a decreasing filtration, so it's indexed by integers. And as my integer increases, I get smaller and smaller subspaces. And well, it's all happening on finite dimensional vector spaces, and I demand that the filtration eventually becomes 0. And there is some large enough step of the filtration which is all of the vector space. And this functor is helpful in this question of recovering other invariants from the Galois action, in that if you plug in this representation of geometric origin into here, you're going to get the following output. So let me write this here. So, such that d de Rham of cohomology of any smooth proper variety, it recovers the de Rham cohomology of the very same variety with its Hodge filtration. So it's the filtration associated to the stupid filtration on the algebraic de Rham complex. And in particular, it's a filtration whose associated graded pieces are cohomology of sheaves of differential forms. So in particular, you see that if I'm thinking of a secret variety, and I just give you its representation of the Galois group on its end cohomology, you can run this machine to guess what are the Hodge numbers of my variety. And these are exactly pieces appearing in the Hodge decomposition if you base change this variety to complex numbers. Right? And it turns out that this is a really fruitful principle that, well, it's unsurprisingly called p-adic Hodge theory, that some invariants of Hodge theoretic flavor are recoverable from the arithmetic data of a Galois action. Right? And basically the topics of the rest of my talks, the topic of the rest of my talks will be trying to explain a rather refined version of this construction happening over, which would work not just for single Galois representations, but for local systems. And along the way, we'll further review how this de Rham in this particular classical setting is constructed. So, but the title of my talks was p-adic Riemann-Hilbert. So let me try to explain what does this have to do with any kind of Riemann-Hilbert. But before I do this, are there any questions especially about the overall structure of what we're doing. Please.
Does this DDR functor lose a lot of information?
Very good question, it does. And great. So, in fact, one of the key kind of points of what we'll do is we'll try to construct a refined version of the functor which will lose less information, but it should come clean that we will, at least as of now, there is no other version of p-adic Riemann-Hilbert which will be an equivalence of categories. And well, in a way, I'll try to argue that for what we're doing here, this is not such a terrible problem, but there are very interesting questions along these lines, which I think so far are completely unanswered. Okay. So, what about p-adic Riemann-Hilbert correspondence? So, let me just very briefly on this board summarize the complex Riemann-Hilbert correspondence, and then we'll try to transport this into a p-adic world with appropriate modifications. So, as Christian explained this morning, if I had, let me just use a different letter to distinguish from p-adic things. So if I had a, let's just for simplicity say, smooth proper variety over C. Then C local systems on it. They were in bijection with vector bundles with flat connection. Okay, and so here, since my variety is proper, there is no condition on regular singularities. It's all, so there is no divisor. It is already its own identification. And for what I'm going to do, let me think of this equivalence as partially encoding comparison isomorphism between two different homology theories which you can attach to varieties over complex numbers. Namely, suppose I had a family of varieties, say Z over Y, which was smooth and proper. It's actually so the thing which gives rise to a local system. And again, as Christian mentioned, this is one source of objects on the left, so I can consider the local system of cohomology with C coefficients in some degree. And one of the features of this correspondence is that it carries this local system of singular cohomology to the analogous structure which encodes the variation of drunk cohomology. So it's the relative drunk homology of C over Y, equal to its Gauss-Manin connection. So it's the you take the relative algebraic Durand complex of Z over Y, and you push it forward to, you take its I-derived push forward down to Y. Right? So in that way, this Riemann-Hilbert correspondence, it remembers that these singular and drunk homology were related. Okay. And somehow, since we're trying to extract some quadriadic information from some information which lives more on the Etel side, this feature will be crucial for us when we'll be trying to come up with a p-adic analog of the Riemann-Hilbert correspondence. Okay? So, how will the p-adic analog of Riemann-Hilbert correspondence look like? So, what is my setup? So let's say that now I have some variety S, which lives over, let's say for now it will be QP. Starting from tomorrow, I'll work over slightly larger fields, but here, just for notation and simplicity, let me stick to QP. And say this was smooth and proper. Sorry, let's say this was just smooth. So what could be the two sides of my Riemann-Hilbert correspondence? So if you forgot all the previous setup, you could try to generalize this very literally. And then instead of complex numbers, you would try to take some algebraic closed field which comes up in p-adic geometry. And this will be a very valid and interesting question. And it's, I think so far there are many very interesting and completely open basic questions about it. It's It's a subject which is currently called basically p-adic Simpson correspondence. But we're not quite going to go into that, because I said that I really want to study local systems which are defined over some non-closed field. So I want that to appear as one side of my correspondence. So on the one side, I'll have all étal QP local systems. On S. Now, what should I see on the other side? So, just by analogy, I could try to put down some kind of vector bundles with a flat connection. And this is a valid thing to do. So let me first do that. So let me introduce a name for them. So now there is a discrepancy with the complex numbers in that here on the left, on the p-adic side, or on the étal side, I'm really looking at something much more refined than just topological local systems, because now Galois group of QP also participates in this object. On the right-hand side, some arithmeticity is appearing, because now I look at vector bundles with a flat connection, which are defined over S over a non-closed field QP. But I claim that I should get more on the right-hand side, more structure on the right-hand side from this additional action of the Galois group. And I'll try to, one of the key points of what I'll say later will be to emphasize why this structure might be given to me. And so this additional structure is this Hodge filtration which I saw here. So, and filtration. So it's a filtration by sub-bundles with the same numerology as before, so it's an increasing one. So some large enough piece of the filtration should be all of the bundle, which should convert to 0. And moreover, I want all of these, I want all of these to be sub-bundles in the sense that quotient by each of them should itself be a locally free sheaf. So if I restrict to any point, then the maps on fibers should still be inclusions. So it means that it's equivalent to saying that Fi mod each next term is a vector bundle itself. So it's a collection of sub-bundles with this property. And now it should interact in a particular way with the connection. So let me introduce notation for the connection. And it should be exactly the familiar condition of Griffith's universality. That connection of the ith term of this filtration, the connection should not quite preserve the Hodge filtration, but it should bump it up into by at most 1 in the Hodge filtration. Sorry, in this filtration. Okay. And so one first version of the p-adic Riemann-Hilbert will be a functor, which I'll denote by the same letter. From local systems to these gadgets. And it crucially will have a similar property that will relate two cohomology theories of families of parameters. Such that if I feed into it, so again, I had some family of varieties. If I feed into this local system of cohomology, I should get back the vector bundle of relative to Riemann cohomology, now equipped with the Gauss-Manin connection, and now this filtration will be the Hodge filtration. And it's a fundamental fact called Griffith's transversality that this condition is satisfied by the Hodge filtration. Okay? So this relation is a generalization of what I had over for simple representations of the Galois group, and but now there is this additional connection which you might expect to appear in Riemann-Hilbert. Right? Are there any questions about this first structure which should exist and we'll see exists?
So in this case, this Hodge is just defined by the truncation.
You mean in the case when there is a family of varieties? Yes, exactly. So there is a relative drum complex, and you just take its two-bit truncations. But I also claim that there is this abstract functor defined using p-adic watch theory, which we'll discuss, which magically outputs for you a vector bundle of Hodgkin equation. But now one question which already came up is how far this functor is from being an equivalence. And I claim that just by staring at this without even knowing anything about this functor, we can convince ourselves that this functor must be quite far from equivalence. And this is going to be probably my final remark before I start. And this will motivate the fact that we actually should look for something finer, and I'll define what this finer thing is, and that finer thing will be more deserving of being called the p-adic Riemann-Hilbert correspondence. But what's the issue of this functor? So let me put this here. So what do we want of a Riemann-Hilbert functor? So it would be nice if at least this functor preserved ranks. So a local system will be given rank, went to a vector bundle of the same rank. I mean, ideally it should be an equivalence, but at least it would be nice if it preserved ranks. And for instance, if it was compatible with tensor products. Right? All these properties were true for the Riemann-Hilbert which Christian. But I claim that there is no way that d-de-Rham is compatible with satisfies these two properties. Right? And be monoidal. So monoidal is just a term which means that if I apply this functor to a tensor product in two local systems, then I should get back the tensor products of evaluations of the functor on both local systems. So why is this? We can already see in this example where my base variety is just spectrum of QP, and so local systems are just representations of the Galois group. So let's consider the following example. So let's say that my base variety is, then again, local systems are just representations of the Galois group of this. Or sorry, let me save myself some effort and let me cheat slightly and do work over a slightly larger p-adic field where I joined a p-fruit of unity. So then again, I'm still talking about just about representations of this group, of the Galois group of that. So then let me consider the following representation. So it will be the QP of -1, which is just the inverse of the cyclotomic character. Okay? Which is what appeared in Gleb's talk. And it also arises homologically in that it's the second homology of P1. With coefficients in QP. It's basically equivalent to Gleb's computation of the fundamental group of GM, that the action on the second homology of P1 is by the inverse of the cyclotomic character. Okay, so now where is this carried into the functor d-de-Rham? Well, it should better be carried to de Rham homology of the same variety with its hot filtration. So let me just denote this field K for brevity. And so this should be second de Rham homology of P1 over K. So this is just K. And Hodge filtration there, it's the only interesting graded piece is in degree 1. So the Hodge filtration should jump at degree 1. So F1 should be all of K, and F2 should be 0, right? Because in the Hodge decomposition for P1, the only interesting term is H1 of omega 1. All right? So this character of the Galois group gets carried to this filtered vector space. But then if this functor was always preserving ranks and it was monoidal, let's think what it would have done on the square root of this character. So what does it mean? Since I adjoined p power roots to my field, it makes sense to the cyclotomic character or the inverse of it. It goes into it's congruent to 1 mod p. So I can, at least if p is larger than 2, I can extract the square root of it. But then the tensor square of this would be this filtered object where the fluctuation jumps in odd degree 1. But this is impossible. Right, because d-de-rum of this guy would have to be also a one-dimensional vector space where the fluctuation jumps somewhere, and then the fluctuation on the standard square would have to jump in twice that degree, but 1 is an odd number. So this is impossible. And oh, sorry, I'm over time, but let me just finish orally that somehow the true version of p-adic Riemann-Hilbert will have to accommodate for the fact that there are these strange representations which kind of they want to behave like Hodge structures, but where weights are not integers, but rather some p-adic numbers really. And so this is what the p-adic Riemann-Hilbert will try to do. But we'll get into this carefully in studying each one. Sorry, I'll stop here.
So you alluded to some extra conditions on arithmetic representations that aren't obviously satisfied. I mean, if you want to write to a layer off, feel free, but I was wondering if you meant to say.
Oh, you mean what conditions I had in mind? Well, I meant having iteration of Hodge structures. And to be clear, I'm not going to prove that. It will be wonderful to prove. We're going to start approaching it. And then I'll try to say at the end what will be the obstacle which so far as yet to be overcome. There's also integrality, but that I have absolutely nothing interesting to say. All right, is this the kind of answer you want to
Oh, please. You mentioned that the relative Fontaine-Mazur, I think, is basically as complicated over punctured curves as it is in general.
Oh, sorry, this was not a. I'm not saying that there's a formal deduction from the case of curves to it, but yeah.
Yeah. But I was wondering if, maybe more can be said in genus 1 case.
Sure, yeah. If it's non-punctured, genus 1, then I think we can just prove it right away because so this conjecture which I already raised, it's quite clear for abelian representations of the fundamental work. So since I'm over QP bar, they all come down to rank 1 representations. And they're basically, all of them, in fact, have to be, they have to have finite monotropy by an argument kind of similar to what Gleb described. And so for elliptic curve, it's genetic fundamental group is abelian, so this could be the case. Since I'm working with some system. Yeah. But as soon as you puncture it just once, I think it becomes.
Is there like a singular version of like this kind of process? For example, if you have like f(x) to f, like this is not
Right. So there is a version which is being developed by Bott and Lurie, where here you would be allowed to feed an arbitrary constructible sheaf. Right. And but here what I'll talk about, I said that there's going to be some refinement which will lose less information, and their thing is a version of that. So there's a version, but it's currently in progress for constructible sheaves.
the right hand side would be some kind of analog of Hodge 1.
Right, exactly. But I should say I don't know much about it.
Questions? Great, what's next session?
Sorry, I think I failed at the writing large challenge.
No. I think it will be good enough.